Hello, Assalamualaikum warahmatullahi wabarakatuh. I hope you have a good rest in between the semester because semester 2 is more challenging. Yes, and today we're going to start with chapter 1 of our new course, Physical and Organic Chemistry, TST0925, with lesson 42, Concept of Enthalpy. I'm sure you know what is the meaning of endothermic and exothermic by now. But how are we going to explain them using the energy profile diagrams? We need to be able to state the standard conditions and define the enthalpy of reaction, as well as defining enthalpy of formation, combustion, atomization, neutralization, hydration, solvation, sublimation, solution. We also have to define lattice energy and explain qualitatively the effect of ionic radius and the charge on the value of lattice energy. When we talk about thermo, we will associate it with heat. We have been using petroleum in our cars to generate electricity, but at the same time, we generate heat energy, excessive ones. So when the reaction is incomplete, most of the energy is changed into thermal and light energy. Let's go further to understand this. I remember when our car broke down in the middle of the highway at night. A kind man stopped and gave his car to me and say, "Take your children home for tonight. Your husband and I will sort out the problem." That night, that kind man eventually stayed at my house and we came to his wedding the year after that. We became best friends. Eventually, he brought a lot of water supplies in his car, and my husband and him drove our overheating car and stopped every 1 or 2 kilometers to make the machine cool down and replace the water so that the cooling system is restored. The world is getting hotter because of the machines that we created. Heat absorbed by the Earth is greater than the heat released to the outer space. We actually release a lot of heat that makes our Earth has become a greenhouse, a very large one. Greenhouse is good for plant, but it's not good for the whole Earth. Read about it in biology. What happened is when the Earth is overheating, the kinetic energy will become lesser. And when the momentum is lower, it will orbit the sun slower. As the Earth moving slower, it will skip the orbit and move closer to the sun. You can imagine that would be Hari Kiamat. This event will lead to the end of our planet as described in Surah At-Takwir. Let's look at the verse. A'udzu billahi minasyaitonir rajim. I will go straight to verse number 6. Wa idzal biharu sujjirat. The meaning is, Allah says, and when the seas are filled with flame, flame is associated with heat, and heat will accumulate earth at the end of time. Let's look at the most northern part of the earth, Arctic. In 1980, I was just 2 years old back then, the ice accumulated more than half of the region. But in 2012, I believe there's a movie about the end of the world named 2012. You can see the ice is getting smaller and smaller every single year. At a constant pressure, when a substance changes, the enthalpy is the heat and work that is needed or released because of the change for the substance. So thermochemistry is a study of enthalpy changes in chemical process. Chemical energy is in the chemical bonds. So how are we going to measure the enthalpy changes? Using this formula, delta H reaction is the enthalpy for the reaction. That is equals to the total enthalpy of formation for the product minus the total enthalpy of formation for the reactant. Let's look at an example. So if you have ammonia react with fluorine gas forming hydrogen fluoride and nitrogen trifluoride, given the standard enthalpies of formation negative 46, negative 269 and negative 114. Where is the enthalpy of formation for fluorine gas? Fluorine gas is at standard state. So here it says the standard enthalpies of formation of all elements are 0. So the elements must be at standard state, gas. Here is the balance equation, and the total enthalpy for products is 3 times negative 269 plus negative 114. Okay, minus by the total enthalpy of formation for the reactant, which is negative 46 for ammonia. And the answer is negative 875 kilojoule per mole. We are using this formula from the previous slide. You can also do question number 2 in the tutorial at the back to exercise a similar kind of question. Now, there are 2 different types of enthalpy. Endothermic and exothermic are the terms you are familiar with. Exothermic releases heat having a negative enthalpy, whereby the total enthalpy of reactant is larger than the total enthalpy for product. The example that is clearly seen for us is combustion. It releases heat, neutralization, and dissolving of sodium hydroxide pellets. Whereas, on the other hand, we have endothermic, which absorb heat. The enthalpy is positive, whereby the enthalpy total for product is larger than the total enthalpy for reactant. Example of this kind of reaction is dissolving ammonium nitrate in water and also mixing ammonium thiocyanate and barium hydroxide crystals. Example of an exothermic reaction is the combustion of methane producing carbon dioxide and water. The example of endothermic is the transformation from the ice to water, having a positive 6.02 kilojoule. You need to be able to draw this energy level diagram for both exothermic and endothermic reaction. So As you can see, for exothermic reaction, the reactant would have a higher enthalpy compared to the product. Therefore, the delta H would be negative. For the axis, don't forget that you are plotting enthalpy or heat change against reaction pathway or reactant and products. For endothermic, you can see that the reactant would have a lower enthalpy compared to products, making the delta H is positive. Now we are going to introduce to you the thermochemical equation. The equation not only must have the phase, solid and liquid here, but it also must have the delta H at the back. So a thermochemical equation is a chemical reaction equation that includes phase and also the enthalpy or the heat of reaction delta H. Example 1.2, please write this in your book. H2O solid, this is ice, producing H2O liquid, this is water. This reaction happens in your soda water, your Coke. Delta H must be written at the back with positive 6.02 kilojoule per mole. This equation is trying to tell us that when 1 mole of liquid water is formed from 1 mole of ice at 0 degrees Celsius, the enthalpy change is positive 6.02 kilojoule per mole. Now you don't need to have that mole because we mentioned mole earlier in the sentence. For reverse equation, the magnitude of delta H remains the same, but the sign changes. Now, when we want to make that water become ice again, we put it in the freezer, and we are going to release the same amount of heat, 6.02 kilojoule per mole. But here, we put the negative sign. Before we look at the definition of enthalpies, let's revise your chapter 6 of your Form 1 syllabus. I just looked at my daughter's book just now. What is this? It's the smallest thing on the earth. Yes, it's atom. It's element. Element is the basic unit, the basic thing, right? Okay. Next, what is this? This is molecule. Yes, it's a compound whereby you have a few atoms bonded together covalently or ionically to become a compound. And then what is this? It's a mixture. There is atom, small atom, there is big atom, they can be molecules, so it is a mixture. Alright, now let's proceed to the definition of enthalpies, and you can see there what is constituent element, the thing that comes from its basic shape or basic thing, and also compound. Compound usually refer to the product. Out of many kinds of enthalpy, 10 we have to learn and define. Enthalpy of formation, combustion, solution or solvation, hydration, neutralization, atomization. Ionization energy IE and electron affinity EA are the ones that is familiar. You have learned it in chapter 4 previous semester. Please look back at it. Enthalpy of sublimation is new, and lattice energy is important. Enthalpy of formation is the heat change when 1 mole of a compound is formed from its elements at their standard states. Let's look at the example. the 1 mole of substance that is formed is H2O in the form of liquid. It was formed from the combustion of hydrogen gas. It has the enthalpy of formation equals to negative 286 kilojoules per mole. Remember, we have applied the standard enthalpy of formation for any element in its most stable state form is 0. Previously in example 1.1, whereby we know that F2 gas has the enthalpy of formation equals to 0, O2 gas also 0, Cl2 gas is also 0. Notice here that the 1 mole of substance formed is at the product. Whereas for the second enthalpy, let's look at enthalpy of combustion. It's the heat released when 1 mole of substance is burnt, completely in excess oxygen under standard conditions. It is talking about carbon now. Carbon must have 1 mole. It is burnt in oxygen excess, O2 gas, and it will form CO2 gas. The delta H combustion is equals to negative 393 kilojoules per moles. Please note where the 1 mole is. For formation, the 1 mole is for product, and for combustion, the 1 mole is for the reactant that is burnt. Enthalpy of solution or solvation is the heat changes when 1 mole of substance dissolves in water under standard condition. For example, the potassium chloride solid, when it dissolves in water, it will become aqueous, right? So there in the slide, it shows here the potassium chloride solid becomes potassium ion aqueous and chlorine ion aqueous, having the delta H solution positive 660 kilojoule per mole. Basically, the heat absorbs here. The fourth enthalpy is enthalpy of hydration. The heat released when 1 mole of gaseous ion is hydrated in water under standard conditions. Standard condition means that it exists in the condition where it is 25 degrees Celsius and 1 atm. That is standard condition. Right. So we know here that the sodium ion, when it hydrated, it becomes aqueous. So the enthalpy of hydration of it is negative 406 kilojoule per mole. Chlorine ion would have negative 363 kilojoules per mole. The solvation process is very related to how ionic crystal is dissolved in water. Water, being a polar molecule, when an ionic compound dissolves in it, the positive end of water will attract it to the negative ion, whereas the negative end of water will be attracted to the positive ion. And electrostatic forces will exist between the ions and water molecules. This will release the hydration energy. This phenomenon is called hydration, and the enthalpy change associated with it is called enthalpy of hydration. And in both figure here, you can see that water molecule in band shape is attached to this anion and this cation according to their polarity end. In your figure 1.4 of the course book, you can see that the electrostatic force is shown in the dotted lines. Here, for cation, which is attached to the negative end of the water, and also here for the anion, which is having electrostatic force with the positive end of the water. The fifth one is enthalpy of neutralization. This time, it is the heat change when 1 mole of water is formed from the neutralization of acid and base under standard conditions. So you can see here, in the neutralization of hydrogen chloride and sodium hydroxide, the 1 mole we're going to find is at water. The water must have 1 mole in order to have the enthalpy of neutralization, which is now negative 58 kilojoule per mole. Next is enthalpy of atomization. The definition is the heat change when 1 mole of gaseous atoms is formed from its element under standard conditions. So the reactant must be the element in standard state and is going to be formed into gaseous form. For sodium, the enthalpy of atomization is positive 109 kilojoules per mole, but for chlorine, since it came from gas, okay, it would have a slightly more amount of heat, positive 123 kilojoule per mole. Do you remember what is ionization energy? It's the energy required when 1 mole of electron is removed from 1 mole of its gaseous atom. So the first IE is positive 740 kilojoule per mole for magnesium because you are removing the first mole of electron. And the second IE, you're removing the second electron to make it Mg2 plus, right? It is higher, positive 1400 kilojoule per mole. Now, electron affinity is the heat change when 1 mole of gaseous atom gains 1 mole of electron to form 1 mole of gaseous ion. Wow! So many 1 mole, 1 mole, 1 mole, 1 mole. Basically, you have to make sure that there is 1, 1, and 1 mole for each of these elements in the reaction. Oxygen gain 1 mole of electron to form 1 mole of negative ion or minus, and it releases energy as much as 142 kilojoules per mole. And then the second electron affinity will make the oxygen becomes oxygen O2 minus. Okay. Okay, for sublimation, the enthalpy of sublimation is the heat absorbed when 1 mole of substance sublimes, meaning the phase turns from solid straight into gas, to form 1 mole of vapor under standard conditions. For example, the solid sodium metal is transformed into gas immediately here. Okay, the delta H sublimation. Here, since it is also delta H atomization, we put A. It is equals to plus 109 kilojoules per mole. For iodine solid, it turns directly to gas and the delta H sublimation is positive 106 kilojoule per mole. The last one is lattice energy, heat change when 1 mole of solid. This solid must be an ionic compound. It is formed from its constituent gaseous ions. So when you have the sodium ion in gas plus chlorine ion in gas, it will form ionic solid sodium chloride. The lattice energy is negative 771 kilojoules per mole. Lattice energy changes are large and the values are negative because more energy is needed to be released to form the ionic solid. The stronger the attraction between the ions are, the larger the amount of energy needed to be released. The lattice energy becomes more negative or bigger as the ionic charges increase and the ionic radii decreases. There is a stronger attraction between small, highly charged ions, so the delta H would be more negative or bigger. Now let's compare the lattice energy between sodium chloride and sodium bromide. Since the cation is the same sodium, we compare between chlorine and bromine. Which ion is larger? The bromide ions are bigger, so the distance between the center of the bromide ion and the center of the sodium ion are further away in sodium bromide. This increases the distance and weakens the forces of attraction. Hence, the lattice energy becomes lower. You can see sodium bromide is negative 733, sodium chloride has negative 771. The second comparison that we want to do is between sodium chloride and sodium oxide. Here, chlorine is negative 1, oxide ion is negative 2. Oxide ion has more negative charge. The higher the negative charge, the smaller the ion, the more negative the lattice energy is. If you can see in the diagram here, O2 minus has 126 picometer of radius, smaller than chlorine ion 167. So the center of the negative ion O2 minus is near to the center of sodium ion, making the attraction is greater. So the lattice energy would be more negative. There would be more energy needed to be released. So the lattice energy for sodium oxide is negative 2478, very high compared to sodium chloride, negative 771 only. The third comparison that we're going to do is between calcium difluoride and calcium oxide, whereby the enthalpy for calcium oxide is much greater due to the charge on the ions. Positive and negative ions in calcium oxide carries two charges, positive 2 and negative 2, whereas for calcium difluoride, the calcium carries 2 plus and fluoride carries 2 negative 1. So the strength of the attraction is much greater in calcium oxide. Therefore, it needs more energy to overcome the electrostatic attraction. Hence, the lattice energy is greater, negative 3,640 kilojoules per mole. Now, between sodium chloride and magnesium oxide. The size itself for magnesium is smaller than sodium ion. Oxide ions also is smaller than chloride ion. That will make the distance between the ions closer, making the attraction stronger. And then the charge of magnesium 2 plus, oxide 2 minus, 2 and 2. It's even stronger compared to sodium and chloride 1 and 1. So here the lattice energy would be much greater, negative 3,795 compared to sodium chloride, only 771. Let's do example 1.4a, compare the lattice energy for potassium chloride and calcium chloride. So which one has a higher lattice energy, a more negative lattice energy? It would be calcium chloride. Why? Because calcium 2 plus ion has more positive charge compared to K plus, since it has also a smaller size compared to K plus. Therefore, calcium chloride would have a higher lattice energy. Let's compare lithium oxide and lithium fluoride. Lithium oxide, the oxide ion is 2 negative, whereas lithium fluoride is 1 negative. So we predicted lithium oxide would have a larger lattice energy because the attraction between F minus and lithium plus is +1 and -1. But in lithium oxide, there are 2 positive charge and there is 2 minus charge. The 2 minus charge is considered a higher charge. This makes the strength of attraction between the two centers of the positive and negative ion in lithium oxide stronger, making the lattice energy larger. Practice 1.1. Let's do A, combustion of the ethylene. So C2H4 is a gas form and it will be combusted with oxygen gas. It will produce CO2 and H2O. CO2 is also in gas, H2O is in liquid form. How many carbon do we need? 2. And how many hydrogen do we need? 4. So this is 2. So how many oxygens are all together? 2 plus 4 is 6. So this would be 3. Now this is a balanced equation and you have to add delta HC equals to -1411 kilojoule per mole. So this is a complete thermochemical equation giving you 2 marks for each of them. I hope this video would help you understand concept of enthalpy. And as the first lesson for semester 2, I hope it's not that difficult and you have much enthusiastic and energized spirit that you are willing to read and learn and do the practice and exercises and the tutorial questions on your own. Please help yourself. Take care and be safe wherever you are, my dear students. Siti Rubaini Mat, your Madam Ruby, logging out for lesson 42. Assalamualaikum warahmatullahi wabarakatuh.